In this lecture, we will continue our study of the basics of group theory. In the last lecture, we met the group, we defined what a group is, and we also saw a few basic properties of the group. Now, it is a standard practice in abstract algebra that whenever we study some new kind of structure, one of the first things we take a look at, right after the definition, is the idea of substructures. And another important thing that we take a look at are mappings between different copies of the structure. Now, while we are not really following the standard abstract algebra route here, because our aim, of course, is different, this particular approach is actually quite useful. So let us take a look to begin with at the substructures which groups have. So we are going to talk about subgroups. So what exactly is a subgroup? Well, what we do is we start with a subset of a group G. The subset H is called a subgroup of G if it is a group in its own right under the same multiplication rule as G. Now, there are two important points to note here. The first is that we have just used the standard abuse of language. That is, we are saying H is a subset of the group G. Of course, what we really mean is H is a subset of the underlying set of the group G, star. However, as I have explained in the last video, we will usually carry out this abuse of language and refer to the group G or the set G as it suits us, because usually it will be pretty clear from the context whether we mean the underlying set or the group itself. Now, the other very important property here, important feature of this definition, is that we are talking about the same multiplication rule as G. Now, this is very, very important. Just to point out how important this is, let me remind you of the very first two examples of groups that we talked about in the last lecture. The first formal example was that of the set of all real numbers under addition. In the next example, we talked about the set of all non-zero real numbers. Now, non-zero real numbers, of course, is a subset of the set of all real numbers. However, for the second case, what we talked about was a different composition rule. The composition rule in the second case was ordinary multiplication of numbers. So despite the fact that the underlying set in the second example there was a subset of the underlying set of the first example, the second example is not a subgroup of the first example, despite the fact that both of them are groups in their own right. So this is important. A subgroup has to be a subset which is a group in its own right, but it has to be a group under the same multiplication rule as the original supergroup. We have actually seen quite a few examples of subgroups in the last lecture. For example, we started with the big group GLNR, the set of all n by n real valued non-singular matrices. And of course, there the group product rule was the standard multiplication of matrices. We then went on to talk about SLNR, where the elements were matrices which had determinant 1. Of course, every such matrix is a matrix with non-zero determinant, so the set underlying SLNR is actually a subset of the set underlying GLNR. Once again, with abuse of language, we will just say SLNR is a subset of GLNR. And SLNR, as we had already seen before, is actually a group in its own right under the same multiplication rule as GLNR, namely the multiplication of matrices. So SLNR is a subgroup. Similarly, ON, the set of all orthogonal n by n real valued matrices, is actually a subset of GLNR. It is a group in its own right under the same multiplication rule, so it also is a subgroup. SON is actually a subset of ON, and it's a subgroup of SON, is also a subgroup of GLNR. So we have met plenty of subgroups in the few examples that we had seen before. However, given a subset of a group, what do we need to check to see whether it really is a subgroup? So the things you must check are closure, existence of identity, and that of the inverse to ensure that the subset is a subgroup. So let's just take these one by one. We know that closure works for the original group. That is, if you take any two elements of the original group, multiply them together, you get an element in the group. If you take two elements from a subset of the group, multiply them together, of course it's not guaranteed ab initio that the result is going to be in the subset. The result has to be somewhere in the group, but not necessarily in the subset itself. So closure is one thing you definitely have to check. In other words, what you have to check is that the original group product law, if you were to restrict it to the subset, is it still a binary operation? You should have noted that associativity is one thing we did not list in the things that we have to check. The reason for that is simple. Any three elements you pick from a subset are also elements of the original set. And since associativity works for any three elements of the original set, it also works for the subset, so associativity need not be checked. However, the identity has to be checked for. That is, the original group of course had an identity, and that will also be the identity of the subgroup if the identity happens to belong to the subset. So that is one very important thing that you have to check. And finally, the thing that you have to check is whether, given any element of the subset, its inverse is also in the subset. Of course, the inverse is somewhere in the group. Has to be because of the original properties of the group. But the important thing to check is whether it is also in the subset or not. Only when all these checks are passed is a subset eligible to being called a subgroup. There is a theorem which makes life a bit easier for us when it comes to determining whether a subset is a subgroup or not. Now this theorem goes as follows. If H is a subset of G, and if for all H1 and H2 belonging to capital H, the element H1, H2 inverse, which is guaranteed to be an element of capital G, actually belongs to capital H, then capital H is a subgroup of G. Note that at this stage, when we are using this theorem, we do not at all know whether H is a subgroup. So when we say H, when we calculate this element H1, H2 inverse, the inverse is being calculated using the standard inverse identification in the group G. So H2 inverse is an inverse of the element H2 in the original group, and we are multiplying it from the left by H1, which is also an element of the original group. So there's no problem in calculating this particular quantity. So the theorem goes, if for all H1, H2, H1, H2 inverse also belongs to capital H, then capital H is a subgroup of capital G. Now, of course, this is a theorem, so it requires a proof. But before we go on and prove it, let me give you an example to show how useful this theorem can be. We will use a theorem stated just now to prove a result which we already know, that the group SLNR is a subgroup of GLNR. Just to remind you, to prove this in the standard way, we had to prove that the product of two SLNR matrices, that is two matrices with determinant 1, was a matrix of determinant 1. Then we had to check whether the identity is in this set, and identity being the identity matrix, of course has determinant 1, so it belongs to the set SLNR. And then we had to show that for every SLNR matrix, the inverse not only exists, is in this subset SLNR of the entire set of non-singular matrices. What we are going to do now is we are going to prove the same result using the theorem that we have just stated. And there the proof goes this way. Take any two matrices A and B in SLNR and then form the matrix A times B inverse and check whether it is in SLNR. So, in order to check this, what we need to know is, of course, the fact that both A and B have determinant of 1, and as a result, the determinant of AB inverse, the matrix we are looking for, is det A times det of B inverse, which is det A times 1 by det B, and that's, of course, 1 times 1 by 1, and so it's 1. So, AB inverse belongs to SLNR whenever A and B does. This, according to our theorem, is a proof that SLNR is a subgroup of the original group GLNR. So we are done. Of course, we are using this theorem, but we need to prove this theorem first. So let us now go on and show how a proof of this theorem can be easily obtained from the basic properties of a group. The proof of this theorem goes as follows. We are starting with a subset H of G, which is non-empty, and remember, what we are demanding is for all H1 and H2 that you can pick from capital H, H1 H2 inverse is in capital H. Note that H1 and H2 can be any two elements of capital H whatsoever, and they can of course be the same element. In other words, we can take H2 to be the same as H1, which of course is an element of capital H, and this will imply that H1 times H1 inverse, which is of course identity, must belong to capital H. So, the premises of the theorem ensures that the identity is in capital H. Now that we know that the identity is in capital H, we can take H1 to be the identity and H2 to be any other element small h of capital H. So now H1 H2 inverse, which is guaranteed by the theorem to belong to capital H, simply becomes E times H inverse, which is H inverse. So what we have established is that for every element small h in capital H, the inverse exists in the set capital H. So identity is done, so is inverse. We are left with closure. And for closure to work, what we do is, for any two elements H and H prime in capital H, what we will do is take H1 to be H prime and H2 to be H inverse. Remember, we have just established that if small h is in capital H, so is the inverse. So taking H2 as H inverse is perfectly fine. And then H1 H2 inverse is simply H prime H, and that belongs to capital H. So what we have shown is that the product of any two elements H and H prime of capital H is in capital H. So closure is also done. This completes the proof that once we have this demand that H is non-empty, and for any two elements H1 H2 belonging to capital H, H1 H2 inverse also belongs to capital H, then this subset capital H satisfies all the basic properties that you need for a subgroup, so is a subgroup. For our next example of a group and its subgroups, we turn back to our old friend, the set of all symmetries of an equilateral triangle. Let me remind you that the set consisted of 6 elements: identity, which is do nothing, A, B and C, which are reflections about the medians marked small a, small b and small c in the figure, and 2 further rotations, D, which is a 130-degree rotation, and F, which is a 240-degree rotation. I say further rotation simply because identity itself is also a rotation through 0 degrees. Now in the last lecture we had figured out the entire multiplication table for this particular group, and the table is on the screen right now. So can we identify some subgroups of this group just by looking at the table? In fact, one of them should be very easy to identify. You just pick E and A, the 2 elements, you can see that we are going to get this particular part of the table, EAAE, which is written down here, and this obviously gives you a two-element group. Well, if E and A give you a two-element group, it is easy to see that there is nothing so special about A. You could have obtained a two-element group by just taking E and B as well, or E and C. In each case, we end up with a two-element group, and if you look carefully, you will notice that they are essentially the same as far as group theoretical structure is concerned. The only thing that changes from one example to another is if you replace, for example, the A here throughout by B, you're going to end up with this table. Or if you replace the B here throughout by C, you will end up with this table. So in a sense, they are essentially the same group, just with the elements labeled differently. Now, we will make this notion of the groups being the same with just different labelings much more precise and formal in a later lecture when we talk of isomorphism of groups. But for the time being, I am pretty sure that you can understand what I mean by this. Well, if I were to take a bigger subset, can I find a subgroup? For example, if I took E, A and B, then we would get these 9 elements in the multiplication table. But one look at it will immediately tell you that this cannot be the multiplication table for a group. For example, this element A times B is D, which is not in the subset that we are looking at. So closure fails right in front of our eyes. So EAB is not a subgroup. There is a bigger 3-element subgroup here, which happens to be the subgroup consisting of the rotations E, D and F. If you just took those 3, you will find a nice multiplication table, which you can easily identify as one forming the multiplication table for a group. So just to sort of illustrate that, you can easily see that the system is closed. You are not going outside E, D and F here, so closure is fine. Associativity, as I've already said, you don't have to check. Identity, of course, is in the set. E is in the set. And then, what about the inverse? Well, D has an inverse which is F. You can see that from here. And F, of course, has an inverse which is D. So, this subset EDF, the 3 rotations, form a perfectly nice subgroup. Now, actually, I should also stress that these are not the only possible subgroups of this group. There are 2 others which are actually right in front of your eye, and they are so simple that it's often the case that we miss them. One such subgroup is just one element, just the identity. So if you take the identity alone as a single element subset, it's easy to check that all the properties of the group are followed. Right? Identity times identity is the identity, so closure is followed. Associativity is trivial. Existence of the identity is trivial because that's the only element you really have in your set. Identity is its own inverse, so the inverse is also in your set. So that is a subgroup. In fact, that is not only a subgroup for this particular group, subset containing the identity alone is a subgroup for every group. Then there's another subgroup which every group has, which is the whole group itself. Remember, in the definition we said H has to be a subset of capital G. Nobody said anything about it being a proper subset. So G itself is its own subgroup. So these are 2 trivial subgroups which every group has. Any subgroup other than that are what are called non-trivial subgroups. So our example, the set of symmetries of an equilateral triangle, have a total of 6 subgroups, 2 of which are trivial. The non-trivial ones are the ones you can see on your screen right now. In fact, all the non-trivial examples here have a special property. They are examples of something called cyclic subgroups. Cyclic subgroups happen to be very, very important part of group theory, and we are going to discuss them in brief now. While we are at it, we are also going to talk about something called a presentation of a group, which is, well, just a way of presenting the group. Instead of specifying all the elements of the group and the multiplication rule, the presentation essentially tells you what the building blocks of a group are. So let us start with cyclic groups. Now for a general group capital G, if you pick out any element small g from capital G and take all its integer powers. Now what does an integer power mean? G square of course means g times g. G cube means g times g times g, the standard way positive integer powers are defined. In addition, you have to define g to the 0 to be the identity, and you have to define g to the minus 1, well, in the way it's written, as the inverse of g. And then g to the minus 2 will be the square of the inverse of g, that is g inverse times g inverse, and so on. So this set of all integer powers of g to the k, where k belongs to a set of integers, is a subgroup of capital G. It's called the cyclic subgroup of small g. So if you pick a different element, you may very well end up with a different cyclic subgroup. Now a cyclic subgroup, by its very nature, is always abelian. That's pretty easy to see, because when you multiply two elements, g to the m times g to the n, what you're doing is you're multiplying mg's and ng's together. And because of associativity, you can just say that this means you're multiplying m plus n g's together, and you are going to get g to the m plus n. Now, a very special situation occurs when the group G is finite. Now, if the group G is finite, then this apparently infinite set g to the k for all integers k cannot be infinite, right? Because there are only finite number of elements to play with. So this set then must have repetitions. That means there must exist natural numbers m and n such that g to the m must be the same as g to the m plus n. And because g to the m is a group element, it has its inverse, you can cancel by it. This immediately tells us g to the n has to be identity. So for a finite group, if you take any element and keep on raising it to higher and higher positive powers, you are bound to hit the identity somewhere down the line. Just to point out that this is not necessarily true if you are going to talk about an infinite group. For example, if you take the element 2002 of GLNR and keep on raising it to higher and higher powers, you are going to get a matrix with larger and larger elements, and you are not going to get the identity ever. So this result that we are talking about is guaranteed for a finite group. For an infinite group, it's possible that some elements, when you repeat them large enough number of times, you do get to the identity. But for the generic element, this may not be the case. But for the finite group, this has to be the case for every element small g. So this means that for a finite group, again, the set small n belongs to capital N, which is those natural numbers for which g to the n is e. I'm saying if this set is non-empty, because I'm talking of both finite and infinite groups in the same breath, although for finite groups this set is guaranteed to be non-empty. For infinite groups, it may or may not be, depending on which particular g or small g you have picked. But if this set is non-empty, there is a non-empty set of natural numbers. It's a very important and almost trivial property of natural numbers that all non-empty sets of natural numbers have a minimum. And let's say this minimum is r. So small r really is the smallest positive integer to which power you can raise small g to get to the identity. Now, for such a situation, this r is called the order of this element small g. Different elements of a group may very well have different orders. The identity, of course, always has order 1 because it is already identity at the first top power. Now, in this case, if such an r exists, this always happens, remember, for a finite group and happens sometimes for specific elements in an infinite group. Then the cyclic subgroup of small g, which is g to the k for all integer powers of k, actually becomes a much smaller set is a set G, G square, G cube up to G to the R, where G to the R is identity. Of course, if you go beyond that, you go to G to the R plus 1, you end up with G back again. And the whole thing begins repeating. So this subgroup is finite in this case. As I have already said, for an infinite cyclic group, G raised to the M times G raised to the N is simply G raised to the M plus N, where M and N are two integers. Now this actually mimics a group which should be pretty familiar, although we did not really talk about this group before. We talked about its bigger cousin. This is a group of all integers under addition. It's very easy to check that this is really a group, and it's actually one of the most familiar groups from childhood, although we did not call it a group then. This word mimics here essentially is saying that whatever you want to learn about this particular cyclic group, you can learn about that just by looking at what happens to integers under addition. We will make this notion of mimics more precise later, as I've already promised, when we talk about isomorphisms. But for the time being, I'm pretty sure you can understand what I mean here. Now, things are slightly more complicated when you have a finite cyclic group. There, if you multiply G to the M by G to the N, you do not get G to the M plus N. Remember, the power for a finite group has to stay within R. What you have is M plus N modulo R. That is the remainder which you get when you divide M plus N by R. So, basically, things keep on repeating after R, as we have already seen. This also is a pretty well-known group. This is a group of integers 1, 2, up to R under addition modulo R. So, the operation is different. It's not just plain addition. It's addition modulo R. Once again, you can easily check that this is a group, and the group has a formal name, is denoted by Z oblique RZ. This notation actually is important in the sense that this is telling you that this is a quotient group. Again, a notion that we are going to talk about later. For the time being, just think of this as a set of all natural numbers up to a particular limit, and the addition rule being essentially the same as that you use in a clock, where after 12 you come back to 1. Here after R you come back to 1 again. Now it is natural to say that these cyclic groups, both the infinite and the finite ones, are generated by the one element small g that we are using to write down the elements. In fact, that is exactly how we will start talking about the generators of a group. An infinite cyclic group is characterized just by a single generator, small g, and we denote this group alternatively by small g within angular brackets. A finite cyclic group, on the other hand, is characterized by the generator small g, and also in addition to that by the relationship that small g raised to the power r is equal to the identity. So it's not just the generator which characterizes the finite cyclic group, it's also the relationship g to the r equals e. The way in which we write this down is we put inside the angular bracket again the generator or generators, as we will see, followed by a pipe sign and then the relationship g to the r equals e. Now these are examples of what are called presentations of a group. A general presentation for a group would be a bunch of generators and a bunch of relations between those generators. So a general group can be presented in this particular form. Within angular bracket, I have this curly g, which is a set of elements of the group which are called as generators, followed by a pipe, followed by capital R, which is a set of relations among these generators. So what are the elements of the group? The elements of the group are what are called words. Words are simply what you can form by treating these elements G1, G2, G3, etc. in curly G as letters of an alphabet. A typical word will be of the form G1 to the M1, G2 times to the M2, etc. etc. Now, note that we are not implying that G1, G2, etc. are different. So you could even repeat the same generator several times and so on. But the group that we are going to talk about is a group formed by these words and associativity taken for granted, along with the set of relationships which is listed out in capital R. Now, we will not spend a lot of time talking about presentations. Presentations are a very, very important aspect of group theory. For example, even in physics, when we use algebraic topological methods in physics, there are lots of groups which arise in that study, and it's basically the presentations of the groups that occur most often there. However, for our present course, representations of groups is not that important, but just for the sake of completeness, let me give you one concrete non-trivial example of a presentation beyond the two examples that we have already seen, that of the infinite cyclic group and the finite cyclic group. So just as an example, we are going to take a look at this particular presentation, where we are talking about a group which is generated by two elements, A and B, and then we have a bunch of relationships between these elements. The relationships that have been listed are A square is the identity, B square is the identity, and AB equals BA. So let us just see which group we are talking about here. Well, we know for sure that there are three elements in our group, at least. Identity has to be in the group, and A and B, the two generators. So we are trying to write down a multiplication table, but we don't have enough information to write the whole thing down. What we can do at least is say that, okay, we have E, A, B as elements. There could be more. That's what these dots here are for. And we definitely know this one row and this one column of the multiplication table, simply because when you multiply anything by the identity, this thing gets returned. So in addition to that, defining relations already tell me some of the products. For example, we can see that this tells me that A times A is E and B times B is E. So out of these 9 slots, there of course could be more, because there could very well be more elements to this group. But at least out of the 9 slots that we have seen so far, 7 have been filled up, 2 are yet to be filled up. Now, there is nothing in the rule so far which tells us that A times B, the element that is sitting here, is going to be the same as any of the elements E, A and B. And remember, the only relations we are allowed to impose on the group are the relations which are listed out here. So the only option we have is to say that A times B is a new element. Let's call it C. So we have put in a C here. But the relationship that AB equals BA tells us that BA must also be C. So we have managed to fill up all the slots that we had here, but this is not the complete multiplication table, because as we can see, at least one more element, C, has to be there. Now we do not know whether the thing will end at C at this stage. So all we know is that we have to extend the table to bring in C. And of course, this row and this column, we know how that gets extended. But there could be very well other elements beyond that. At least at this stage, we have no way of knowing for sure that this is where the thing ends. In fact, if I knew for sure that this will end up being a 4-element group with E, A, B and C as the only elements, then I would have been able to finish the multiplication table simply by using the rearrangement theorem. The rearrangement theorem would have told me that the last element here has to be B, this one has to be A, no repeats are allowed in any row or column, remember, and going along in this way I should be able to finish the entire table. However, at this stage I am not so sure whether my rules tell me that I have only 4 elements. So let's try to analyze the rules a bit further. What should this element be? It's actually C times A. But C times A, C, remember, is both AB or BA. I could write it as BA because that's an that's going to be easy for me to work with. So BA times A. Notice that the bracket here tells me that BA actually gives me C, and that's what we are multiplying by A on the right. But because of the associative property, I can move the bracket from here to here and write this as B times AA. AA, of course, is A square, and my defining relations contain the rule that A square is E. So that's the same as BE, hence is the same as B. So that's why we have put in a B here. Now we can continue further. For example, what is this? CB. For CB, writing C as BA will not really be very useful. We will end up with BAB, and I don't really know how to handle that directly. But instead of writing that as BA, I could write C also as AB, and I will then get AB times B, that's A times B square, that's A times E, hence A. Well, what about this corner? That's C times C. Well, in order to write that, all I will do is write C as both AB and BA. It's easy to see why I have done that, because now the two B's next to each other give you B squared, which according to the defining relation is just identity. So you then end up with A times A, which is A squared, that's E. So C squared is E. And proceeding along these lines, it's very easy to see what these are going to be. AC is going to be B and BC is going to be A. And now note that at this stage I've got 4 elements and I've got a closed set of multiplication rules. There is no need for a new element. So we have found the complete multiplication table. So now we have the complete multiplication table for our group with these two generators obeying these relations. And this multiplication table is that of a pretty well-known group. It's called the group V4 or the Vierergruppe, which in German simply means a group of 4 elements. It is also called the Klein group after Felix Klein, the person who first described its many useful properties. And despite being a rather simple abelian group, it happens to be a pretty important one. The fact that it is abelian can be easily seen from its multiplication table. If you look right down this diagonal and reflect, you will find that the table is symmetric under this reflection, which is a sign that the group whose multiplication table it is abelian. The Klein 4 group actually has plenty of applications, but let us just point out one situation where this will be of use to us. This happens to be the symmetry group of a rectangle. And there the identity of these generators A and B are pretty easy to understand. A is nothing but a reflection along the midline, one of the midlines of the rectangle. B is reflection along the other midline. And since two reflections done one after the other gives a rotation, AB actually is a rotation. In fact, rotation to twice the angle between the lines. This is something which is very easy to establish from elementary geometry. So it's a 180-degree rotation. A square equals E. That's simply because if you carry out the same reflection twice, you are going to get the identity. Similarly, B squared is equals E, and AB equals VA is a standard property for two reflections, successive reflections, along intersecting lines. So this is one case where we can easily identify at least one concrete realization of the group. And it's pretty easy to figure out that the multiplication table would have been the same if it just started with these 3 elements A, B and C along with the identity, of course. Now this is one of the 2 distinct kinds of groups that you can have with 4 elements. Remember, this is exactly what we said at the end of the last class. There we had actually figured out all the possible groups with 3 elements, but we had pointed out that if you had 4 elements, we had just stated that there, you can have 2 distinct kinds of group structure, both abelian. This is one of them. The other one is simply a cyclic group with 4 elements, where the elements are generated by R and the elements are simply R, R square, R cube and R to the 4, which is of course back to the identity. The multiplication table which you can see on the left is a pretty straightforward one. The one important property which I would draw your attention to is that not only are the rows of this table rearrangements of each other, as the rearrangement theorem would definitely force you to have, they're actually cyclic rearrangements. This, of course, gives credence to the name cyclic group, and this happens for all cyclic groups, and that's something which is pretty easy for you to figure out on your own. Well, what about groups of size 5? We will see in the next lecture that a group of size 5 has to be abelian. In fact, has to be a cyclic group of order 5. Why? Well, that's part of a bigger story, and that's what we are going to describe in the next lecture. Until then, bye.